So once that we get established the substitution rule, we can get some general integration formulas from it. So as an example, we can do cosine of anything now but x. So we can go cosine of ax, and that's going to give me 1 over a sine of ax plus c. Similarly with any other of the trigonometric, sine of ax, secant square of ax, cosecant square of ax, secant by tangent with ax on the argument. We can use the e to the ax, and that's going to be 1 over a e to the ax plus c. We can use some of the inverse trigonometric functions. So for example, the integral of 1 over a squared plus x squared is going to end up being 1 over a tangent to the minus 1 of x over a. Of course, you don't have to necessarily learn these formulas. You can always do the integration and find those formulas by yourself. So let's take a look at some of those formulas here and do some of those examples. So we're going to have b to the x, e to the ax, and the integral of 1 over a squared minus x squared. So let's go to the board. So first, let's just remember that b to the x is just essentially e to the x log of b. This is essentially the same thing. And so if we do a chain rule of this, then we're going to get a log, right? So bx prime is just this same but multiplied by the log of b. Okay, so under that idea, we can just think of it as b to the x is just the exponential of e to the x log of b. And using a substitution, we can go and replace this by u. So u is going to be x log of b, and then the u dx is just going to be log of b in here. So the u is equals log of b dx. And so the transition becomes e to the u times 1 over log of b dx. Since we don't have the log of b over here, so we just put it down here and transform this to 1 over log of b du. Now at this point, we can integrate, and of course this is a constant. Log of b is just a constant, so it becomes 1 over log of b e to the u plus c. And that mirrors the formula that we find over here. So as you can see, b to the x, the x is 1 over log of b times b to the x plus c. Similarly, we shown in the previous video the one for e to the ax, and so we can now play with the formulas for different things like the different trigonometrics. So to transform this in one of the trigonometrics that we know, we're just going to factor the a. And so if we factor the a down there, we're going to have a squared, a factor of 1 minus x squared over a squared dx. And so I can take the square root of this a squared, and I'm going to get 1 over a this integral. And now it's looking really similar to the antiderivative of the arc sine, right? But we need to get some finishing touches. So if u is x over a, which is, well, we'll transform that in u squared. Notice. So the u is just going to be 1 over a dx. Okay? And we have the 1 over a over here, so we can just pretty much transition to do everything that we need. So we can just write this as 1 over 1 minus u squared times and then 1 over a dx becomes the du. And then at this point, we know that this is arcsine of u plus c. And now we can just return to the original variable. And this is arcsine of x over a plus c. Okay? And so that's going to match up with the formula that we have right here for the arcsine. Okay. Last but not least, we can do the same thing, but with a constant. So notice that here we have the same thing, but with a constant. So if we transform that to a particular constant, we can just apply directly what we just learned. So 4 minus x squared dx. And so notice that the a is 2. So this is going to just be arcsine of x over 2 plus c. Okay? So depending on whatever you want to do, you can either apply these formulas or do the overall substitution procedure and do the integration. Okay? Now, of course, we just spent quite a bit of time knowing how to do also definite integrals where we have an interval defined in a certain area. That's not something that we're going to lose here. And so there are two different ways to do that. And one of them is going to do proceed and find the antiderivative as usual. And the other one is going to be using a transformation for the substitution rule. So before getting into this rule, let me do an example of the first one. Use another board. So we're going to have the integral from 0 to 1 of x squared plus 3 to the 7 times x dx. Okay, so instead of working with the integration limits, what I'm going to think is, well, first I'm going to think on this integral, and I can solve that by substitution. U equals x squared plus 3, and so the u is 2x dx. I don't have the 2, so 1/2 the u is going to be x dx, and I can transform this into u to the 7 times 1/2 the u. And so this is 1/2 u to the 8 over 8 plus c. And now notice that I can go back to the original variable, 1 over 16 x squared plus 3 power to the a plus c. And so this is going to be my general antiderivative. Okay, but now I can apply fundamental calculus theorem. And by the fundamental calculus theorem, this says that 0 to 1 x squared plus 3 to the 7 is just going to be the antiderivative in 1 minus the antiderivative in 0. But I have my antiderivative here, so this is just 1 over 16, plug in 1, so 4 to the 8 plus c, and then minus, and then plug in 0, 1 over 16, 3 to the 8 plus c. Okay, and that will yield the result in one form. Okay, now let's take a look at what this says. Now the second way of going through the substitution rule with limits is going to be to use the substitution on the limits. So if you see in the substitution, we usually go for the inner function and declare that that is u. So u becomes g of x. So what we're going to do here in the transition is that when we transition to the integral in terms of u, then now my limits are going to be in the image of the inner function. So we're going to plug a in g, and that's going to be my new limit. And we're going to plug in b, and that's going to be my new limit. And so now this is going to be an integral that is only in terms of u, and we don't need to go back to anything because we already transformed everything including limits. Okay, so let's see how that fares with the example that we just encountered. So we have that at the very end, this here is just going to be 1 over 16, 4 to the 8 minus 3 to the 8, whatever that is. But and then again, we have a little bit of information over here. We have that we can also do this as transformation. So if u is x squared plus 3, notice that when x is equal 0, if x is equal 0, u becomes 3. So we can replace 0 by 3 here. And if x is equals 1, then u becomes 4. Okay. And now this transformation here becomes 1/2 u to the 7 du. So now this is my full integral, and I can go and integrate 1 over 1/2 u to the 8 over 8, and then this is going to go between 3 and 4. Okay, also by fundamental calculus theorem. So now this is 1 over 16, and then we're plugging 4 to the 8 minus 3 to the 8. Okay, so any of the two techniques arrive to the same point, whether I'm doing first the full antiderivative and then plugging values at the end by the fundamental calculus theorem, or just transforming fully the integral with limits as well. In part 3, we're going to see some more examples of how this technique is used, and then the geometrical behavior that that's going to imply.